Section 2.2, even and odd functions. This is your notes. In geometry, we learned about two types of symmetry, reflective and rotational. Determine which of the following graphs exhibits reflective symmetry and which has rotational symmetry. Looking for reflective, rotational. For those that exhibit reflective symmetry, draw the line of symmetry using a dashed line. For those that exhibit rotational symmetry, identify the point of symmetry. So first of all, looking at this graph, does this graph have reflective symmetry or rotational? Reflective means that if you draw one part of the graph and reflect it over a line, you'll get the other part of the graph. So this first one definitely has reflective symmetry. And the line of symmetry would be the y-axis or the line x equals 0. I want to point something out, and I'll come back and point that out later. G of x, is there a line you could reflect this over to have symmetry? And the answer is no. But there is rotational symmetry. If I took this here and I rotated it like so, it would be right on top of this other one. That's rotational symmetry. What is the point of rotation? Point of symmetry? It's that little fella right there. This next one, h of x, also has rotational symmetry. I could take this part here and I could rotate it and then match up with this one. That's rotational symmetry. It's the point of symmetry. So this point here, this one also rotational. P of x has line symmetry. The line of symmetry is the y-axis again. Line symmetry is reflectional. I'm going to write reflective because that's what it asks us to write. R, definitely not reflection. Is it rotational? Let's see, if I rotate this about the origin, it's also going to end up working. So this is reflected about the origin. This is rotational. This last one is reflective, with the line y equals x being the line of symmetry once again. Hopefully you can see by looking at those which ones are rotational, which ones are reflective. Above, there are three functions that exhibit reflective symmetry. Reflective, reflective, reflective. And their lines of symmetry are all the y-axis, which we had marked. There are also three functions that exhibit rotational symmetry, rotational, rotational, rotational. And their point of symmetry is the origin, and we have that marked as well. In the boxes, identify the three functions that have reflective symmetry. Those are the ones I highlighted in green, which would be f of x, p of x, and q of x. So identify the three functions that have reflectional symmetry and the three that have rotational symmetry. So rotational symmetry would be g of x, h of x, and r of x. Then in the boxes below each function, list all the specifically plotted ordered pairs. List them in order that they appear from left to right. We're not going to do that last part. We're going to be a little more strategic in how we list these. So this ordered pair here is -4, 1. Write that in the box where I wrote it. The next one is -2, -1. The next one is 0, -3. Write these in the same spatial place that I'm writing them. The next one is 2, 1. And then the last one is 4, 1. Those are the 5 ordered pairs that have huge dots there. Interesting. Check out those numbers. See if you notice anything. I sure do. P of x, if we put those ordered pairs in here, we got 1, 2, 3, 4, 5, 6, 7, 8 of those. Those end up being -6, 4. There's also a +6, 4. There is a -3, -5. It's also a +3, -5. There is a -2, 0. There's also a +2, 0. And there's a 0, 4. Notice anything those points may have in common with each other, like globally or pairing them together? Q of x will be this last function. If I write its ordered pairs down here in a strategic order, I might write them as -5 and 4 is an ordered pair. Oh, 5, 4 is also an ordered pair. Interesting. -3, 0. Oh, +3, 0. -1, 2. Oh, +1, 2. And then 0, -4. Notice any relationships? If I pair these together like so, first thing you'll notice is there's a point in each case that doesn't have a pair. That's because that point is on the line of symmetry. These 3 are on the line of symmetry. They don't have a pair. Any point not on the line of symmetry that's reflected over the y-axis will have an equivalent point, which the y value is the same and the x value changes sign. Got -4 to +4, -2 to +2. That works for all of these x values. Notice the y values don't change on its corresponding pair. Let's check out the points for g of x that were named. We had a -4, a -3, and then we had a 4, +3. We had a -2, -2, and then we had a +2, +2, and then we had a 0, 0. Looks like to me, change the sign of the x and the y values for these ones. See if that fits with the next one. H of x, we got -3, -4 is on the graph. +3, +4 is on the graph. Both signs change. That works. -2, -1. +2, +1. If this sounds familiar, it should, because we did this in geometry. R of x, we have -5, 4, and then in +5, -4. We had -3, 0, and then +3, 0. Change the sign to 0, it's still 0. We had -1, -2, and then 1, +2. I mean, check it out, you know? So let's sum all this up. What observations do you make about all the points on the graphs of the function with y-axis reflective symmetry? Well, if you take the pre-image, which would be, in this case, half of the graph, it's an ordered pair. To get the image, that's the other half of the graph, you change the sign of x and you leave y the same. That's what happens if a graph is symmetric with respect to the y-axis. What observations can you make if a graph is symmetric with the origin? Well, the pre-image, which is half the graph, you change the x and the y values signs. So they have the same values, you change their signs, and that tells you what the image is going to be. So once again, this one here is a symmetric about the y-axis. This little fella here is symmetric about the origin. Numerically and graphically define, numerically and graphically definition of even and odd functions. Even function. Numerically, a function is even if for every point xy there exists a negative xy. Write that down, please. For every point xy, there exists another point negative xy. We left some space because we needed to also describe it graphically. For the odd function, numerically, a function is odd if for every point xy there exists a negative x and negative y. Pause this, write that down. Even function. Graphically, a function's even if it has reflectional symmetry with the y-axis. Graphically, a function is odd if it has rotational symmetry with the origin. Pause that and then write that down, please. So let's check out some examples. Analytically, that means using algebra. That does not mean looking at the graph. A function is an even function if the equation of the function f of negative x can be simplified to the same equation as the function of f of x. Thus, f of negative x equals f of x. So as an example. The directions for this might say something like, determine if this function is even or odd. Right now we're just talking about even. So we are going to determine if it's even. We're going to put a negative x in for all the x's. When you substitute, use parentheses. Simplifying. What's a 3 times a negative x? Well, that's a negative 3x. What's a negative x squared? Well, that's n positive x squared. A negative 3x absolute value of that is going to be a positive 3x. 2 times a positive 3x. You know what? Let me stop right there. Getting ahead of myself. I apologize. Would we agree that this is going to become positive? That's equivalent to me saying 2 times the absolute value of a positive 3x plus x squared. I think we would agree. Is this identical to the original function? It sure is. So what's that mean? It means that the original function f of x is equivalent to putting in a negative x into that function. What can we conclude from that? F of x is even. If that didn't come out to be the same as the original, then it would not be even. Let's check out another. We're going to put a negative x in for each of these x's and see what happens when we do that. A negative x to the fourth is going to be positive. It's going to be positive 2x to the fourth. A negative x squared is going to be a positive x squared. That's as simplified as we can get it. Is that the same as the original? You betcha. So what does that mean? That means that g of x is identical to g of negative x. Had no effect on it putting in a negative. Therefore, g of x is even. Why are we putting in a negative x for this and hoping that it comes out to be the same? because if a function's even, xy is going to have an equivalent point, negative xy. Notice how the y's don't change, but we can change the sign of x. That is why. Let's check out this next little fella. Using your graphing calculator, sketch the graph of p of x on the axis below. Based on the graph, is it even or odd? Explain why. I am going to cheat here because I already have this written someplace. Just going to bring it over. I put this in Desmos. Here we go. And paste. There we go. If you put that in your calculator, you're going to get this. If you didn't get this, and you should take time to put this in your calculator, the reason is, if you have an older calculator like mine, make sure you put the denominator in parentheses. If you have a more modern calculator and you can put the function in as a fraction, it's not going to give you a problem. But if you have to put it in linearly, you need to put the denominator in parentheses because there's more than one term. Using your graphing calculator, sketch the graph. We just sketched it. Based on the graph, is this even or odd? What do you think? Does it have reflectional symmetry with the y-axis or rotational symmetry about the origin? The graph has reflectional symmetry with the y-axis. Therefore, p of x is even. Second part of this says, find an equation for p of negative x. Based on this equation, let's just do that first. Let's find this. So p of negative x was to take the function that we're given, replace every x with a negative. When you substitute, please use parentheses. If you, should make this smaller because I got a lot of writing to do. If you take a negative to an exponent, and that exponent is odd, you're going to end up with a negative answer. A negative x to the fifth is going to be a negative x to the fifth. Multiplying these two together, we're going to end up with negative x cubed over negative x plus 2x to the fifth. Now, is this the same as the original? The original was x squared, x cubed. Ours is negative x cubed. And the bottom is x minus 2x to the fifth. Ours is negative x plus 2x to the fifth. They look to be different. They're actually not. My fifth here looks a little big. You can factor a negative 1 out of the bottom. For that matter, you can factor a negative 1 out of the top. And then if you cancel those, what you're going to find is that this, in fact, is identical to the original function. P of negative x is the same as p of x. Therefore, p of x is even. Cool, 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 cool. Let's check and see what happens if we end up with the directions that say, analytically, a function is odd if the equation of the function f of negative x can be simplified to the negative of this function. Did I answer the question up here? I don't know if I did. Based upon your equation, is p of x the same as it is? We said that it was. Why or why not? Oh, then it says, is it even or odd? and we said it's even, and we have the reason. So we got it all there. So for this one, we're going to do it the same with the same work that we just did the previous one. We're going to replace x with a negative x, just like we did to see if it was even. That should make you happy, because you're going to do the even and odd problems the same. If you're doing them the same, then how are you going to know which one's even and which is odd? Well, let's figure that out. 3 times negative x is negative 3x. A negative x cubed is going to be an x cubed that's negative, plus a negative would be like subtracting a positive. Is this just like the original? Sure doesn't look like it. Could we factor a negative 1 out of this? We sure could. Why would we want to do that? Because now we can see that this part's just like the original. What's different? We're multiplying it by a negative. So in other words, f of negative x is equivalent to negative f of x. This thing that you see here in blue is f of x. We have a negative on the outside of it, just like this had a negative on the outside of it. We got that by putting a negative x into it. So our conclusion from this is f of x is odd. Let me sum up. If you put negative x into this and you end up with the original function, it's even. If you put negative into this and all the signs are the exact opposite of the original, it's odd. Let's do another. This is a little fishy. Got this absolute value in here. We have g of negative x equals 2 times negative x minus negative x times the absolute value of 2 times negative x. 2 times negative x is negative 2x. Subtracting a negative is like adding a positive. It's plus x. Absolute value, we have 2 times negative x is a negative 2x. This, even though this product is negative, when you take its absolute value, it's going to become positive. So this is equivalent to this. Is this identical to the original function? It is not. Could we factor a negative 1 out of each of these terms? We could. Is this identical to the original? And then in turn, are we multiplying that by a negative? Yes and yes. So we can conclude from this that g of negative x is the same as negative g of x. And our global, therefore, is g of x is odd. All right. Another set of examples, different directions. If f of negative x does not simplify to the same equation as f of x or negative f of x, then the function is neither even nor odd. So let's see what happens. Assume the directions for this will be something like determine if the function is even or odd. To determine this, we're going to put a negative x into the original function. Every place you see an x, you're going to put a negative x. If your base is negative and it's raised to an even exponent, it's going to become positive. If your base is negative and it's raised to an odd exponent, the answer is going to be negative. Is this the same as the original? If we factor a negative out of it, is that going to be the same as the original? Is either of these the original or the original with a negative out in front? No, neither is. So what could we say? If we want to be thorough, we would say that f of negative x, that is not the same as the original. F of negative x, it's also not the same as negative f of x. Therefore, f of x is neither even nor odd. Let's do another. Let's put a negative x in for each of the x's. An absolute value is a grouping symbol, so I'm not going to put that negative x in another set of grouping symbols. This one here. Can if you want, don't need it. 2 times negative x, negative 2x. The absolute value of a negative x is positive, and then a negative x squared is positive. Is this the same as the original? No. If I factor a negative out, will this be the same as the original? Also no. So g of negative x is not g of x. G of negative x is not negative g of x. Therefore, g of x is not even or odd. I like those apples. Last example. Let's consider one last example. That's why I said last example. Use your graphing calculator, graph this based upon it. Is it even or odd? Justify your answer. I've already graphed this. Let me go grab it. Copy that little fella. I use Desmos to graph this. Does this look even or odd to you? Looks pretty stinking odd to me because it has rotational symmetry with the origin. So we're supposed to sketch it based upon the graph. Is it even or odd? And then why? So we already got it sketched. I'm going to give the y first. The graph has rotational symmetry about the origin. Therefore, p of x is odd. Find an equation for p of negative x. Based on your equation, is p of x even or odd? Why or why not? Let's figure out what p of negative x is. P of negative x equals 2 times negative x minus 3 times negative x cubed over 2 times the absolute value of negative x. 2 times negative x is negative 2x. Bring down the minus 3. A negative x raised to the third power is going to be a negative x cubed. On the bottom, the absolute value of x is x. It's going to be negative 2x. Subtracting a 3 times a negative x cubed is going to be a plus 3x cubed. And this is over 2 times the absolute value of x. Is this the same as the original? It is not. But I could factor a negative out of the top. I'm going to put that negative all the way out to the front of the fraction. So this is identical to the original. Then there's this negative hanging out here in front. That means that p of negative x is equal to negative p of x. Therefore, p of x is odd. We found p of x. Is it even or odd? We did that. Why? There's the reason why. So, finished. That concludes section 2.2 notes.